So this first lecture, so let me get started right away. So I assume that slides will be made available to everybody, so you should not have to take notes and things like that. I never liked taking notes when I was a student. So my job is to tell you about neutrino physics. This is a topic that has evolved a lot in the last couple of decades or so, and it does drive a large chunk of the experimental physics program today. So it's at least nice to be cognizant of what's been going on in neutrino physics. So this is what I plan to cover in the next 3 lectures. And mostly what I'll talk about today is to try to give you a very quick and very, very biased snapshot of how we got to today. And so I will spend a lot of time talking about the prehistory of neutrino physics. And I'll be using the slides for that because this is a sort of thing that hopefully most of you are familiar with. And so this will be a lot of repetition and stuff that you learned maybe when you were an undergrad or something like that. But I think it's important to get a sense of how progress was made in this field of weak interactions historically, just to give you a sense of where we think we might be going in the future. Then as part of this history part, I'll try to remind you of what are called these neutrino puzzles that plagued particle physics for the last 50 years or so, and they were eventually resolved at the turn of the century. And then, of course, the physics that's responsible for resolving this is the fact that neutrinos have non-zero masses, and they undergo this phenomenon called neutrino oscillations. So I'll talk about that a little bit. And then piggybacking on the neutrino oscillations discussion, I'll try to give you a snapshot of where we are as far as understanding this phenomenon is concerned. And I will try to convince you that that's what drives a lot of the experimental efforts that are going on today. Then I will move towards more theoretical things towards the end and trying to convince you that neutrino physics are non-zero neutrino masses are an interesting discovery because they force us to revisit some of the things in the standard model that we thought were correct and asking ourselves, how are we supposed to be modifying this model in a way to accommodate non-zero neutrino masses? And then I'll try to discuss some of the model building that comes along with that. And hopefully just to give you a sense of what it is that people who do a lot of research on neutrinos concentrate on. So because this is going to be available to you, I try to come up with a very biased list of reviews that people have worked on to give you a sense of neutrino physics during the last, I guess this is getting old now. So this is about, say, 15 years or so. And it does give you a sense of how quickly this field has been changing. And one thing which I hope to convince you of is that if you follow the history of the neutrino, things usually change very, very, very slowly. So progress comes every other decade or so, and somehow we've entered this era where this is no longer the case, which makes neutrino physics particularly exciting today. So let me get started by reminding you of the history of particle physics in the 20th century. A couple of warnings. This is a highly selective list of topics. There are lots and lots and lots of important historical facts that I will omit. I am quite sure that there will be lots of things which I'll say which are wrong, but they are correct in spirit. So hopefully that will be good enough. And again, this is a very biased list of history, but let's start out. For neutrino physics, the most important thing that happened in prehistory was in 1896, when a natural radioactivity was discovered. This is one of these great stories in physics which may or may not be true, but I'll tell you anyway. And so natural radioactivity was discovered by Henri Becquerel, who was doing studies in phosphorescence in uranium salts. And the idea is pretty simple, especially if you're a theorist. You take this uranium salt, you expose it to light, and then you figure out that it shines light after you've done that. So people were intrigued about how that happened, so they were making measurements of that. And the story goes, and this is a part which may or may not be true, but it doesn't matter, that he was doing these experiments, and at one point, he had to do some experiments of phosphorescence. I think he lived in Paris. The weather in Paris is horrible, as many of you might know. So he couldn't do the experiment on a particular day. So he took his samples, he put the samples away in a drawer, and he had to go on a trip. So he came back from the trip, and a long time later, he remembered that, hey, I have this sample that I put on a drawer. I don't know if it's any good or not. So he opened the drawer, and the way that they did experiments back in those days was with a photographic plates. And basically what he did is he had this photographic film, and he put the uranium salts on top of that. And so he opened the drawer, everything was kind of old, so he had this photographic plate, and he decided to develop that. This is actually, that part is true, there's pictures of this. So if you take the photographic plate and he developed that, he noticed that where the little box with uranium salts was sitting on actually had left an imprint in the photographic plate. So that was odd because it wasn't supposed to do that. So of course he repeated the experiment, this time on purpose. So he put the little piece of uranium on top of this photographic plate. He left it there for some time. He developed the plate, and he found out that for some reason, uranium was emitting this magic thing that was leaving an imprint in the photographic plate. So this is a discovery of natural radioactivity. And of course, immediately after that, people started doing lots and lots of experiments just to figure out what was going on. So what is this radioactivity? What does it look like? And if you're doing an experiment, and you found some new form of energy that's being emitted from a piece of material, you start asking questions about that energy. And that's exactly what these people were doing at the turn of the 1800s to the 1900s. And they could ask very simple questions of the radioactivity. So that's what they did. So one thing you can ask is, does the radioactivity that comes out of this piece of material have a sign as related to charge? So is it charged? And that's easy to test. You make a sample where you can emit the radioactivity in a particular direction. You place that in a magnetic field, and you see if it bends, for example. So that's one thing you can try to measure. The other thing you can try to measure is you can measure the properties of the radioactivity by asking how hard is it to contain the radioactivity. And that was actually the first zeroth order thing that they did. And they found out by doing these experiments with lots of different materials that there are three kinds of radioactivity if you classify them by how hard it is to contain the radioactivity. And of course, they gave these things names alpha, beta, and gamma for completely obvious reasons. So there's no mystery between these names. There are three kinds, it's A, B, and C, but you don't want to use A, B, C because that's boring. So you use alpha, beta, and gamma. And of course, alpha radiation, as people know very well, is very easy to absorb. And people also figured out that alpha radiation actually has positive charge. Beta radiation, on the other hand, is a little bit harder to absorb. That means it's harder to contain. So again, the idea is you do the experiment, you put the piece of material here, you put a detector here, and then you put a barrier in the middle. And if it's easy to make the radioactivity not get to the detector, that's easy to absorb. If it's a little bit harder, it's a little bit harder. And if it's really hard, it's really hard. And alpha radiation, as you might know, or you should know, you can kind of stop it with a piece of paper. You cannot do that with beta radiation. You need a little bit more material for that. And gamma radiation is even harder to stop. So that's how they were originally classified. People then also figured out that beta radiation had negative charge for all of the stuff that they managed to study at the time. And gamma radiation did not have any charge, and it was the thing that was hardest to stop. This is kind of step 0 of studying this natural phenomenon of a natural radioactivity. You can do more sophisticated experiments by asking, and before I talk about that, let me remind you that this is in 1896. At this time, we did not know of any fundamental particles. That took 1 year. In 1987, the electron was identified as a thing, as a particle, by studying cathode rays and these tubes that people put an electric field on, and you saw stuff moving one way or the other. So the electron was discovered here, but going back to the radiation, people could also study the energy of the radiation that comes out. And you can kind of understand how you would do that, certainly for alpha and beta radiation, because you can take the radiation, you can place it in a magnetic field, and the bending in the magnetic field will give you some information on the momentum of the thing that's coming out. So by studying that, people figured out a couple of interesting things. For example, alpha radiation usually comes out more or less monochromatically. Beta radiation will come back to, and then alpha radiation was harder to measure the spectrum, but people figured out how to do that later. Okay, so our job is to talk a little bit more about beta radiation. And again, it's important to keep in mind what was going on at the time. In the 1900s, we didn't know quantum mechanics existed. By 1910, we had learned a little bit about quantum mechanics and we were very, very confused. Okay, so that's sort of where we are. And one thing that was going on with beta radiation is people were trying really hard to measure the spectrum of beta radiation. If you read the histories associated to that, this is a very, very confusing time in our understanding of radiation. And you probably know a lot about beta radiation, and you know that the end result of the discussion is that the spectrum of the radiation that comes out is continuous. So a beta radiation happens, you get this beta ray, which now we know is an electron, and that electron has a continuum of energies. People did not know that for a very long time. So it's only in 1914, so about almost 20 years after radiation was discovered to begin with, that somebody did a set of experiments that established beyond reasonable doubt that the spectrum was continuous. Okay, so that was a fact, and it took a long time to establish that fact. Now, this was very, very confusing. When they figured out that the spectrum of beta radiation is exactly continuous, they were surprised, and that's why it took people a long time to convince themselves that this was actually correct. And there are lots of reasons to be surprised, and I will mention the two obvious ones. The first one is the following. One is that this was clearly a quantum mechanics phenomenon, and if you remember the old history of quantum mechanics, usually when you have spectra of radiation coming out from some physics process, like say atomic lines, you get these discrete spectra. Actually, that's where the word quantum comes from. So this one looked different, so people were puzzled by that. A more serious concern, of course, was energy momentum conservation. So you probably know the story. After we learned a little bit more, we knew that this process could be properly defined as some atom that was converting into another atom, usually an ion because you lost charge, and then an electron was emitted. So regardless of what's going on over here, you can appeal to the conservation of energy and momentum to make a prediction. And the prediction is that this electron that comes out, the beta radiation that comes out, has a very well-defined energy and momentum. You can calculate it. You don't have to know anything about the interactions or what's going on in order to predict very, very strictly that this electron has to come out with a well-defined energy and momentum, and you could calculate that. And just to give you a sense right over here, I will draw a beta spectrum. And keep in mind, this is similar to the rotation curves of galaxies. So here's the beta spectrum that you predict. It's a delta function over here. Here's the beta spectrum that you measure. It looks like that. Completely different. So that's bad. So of course, very, very smart people spend a very, very long time thinking about this. There are lots of... Did I do that? Did I do something weird? I probably did. So let's see. Thank you. So if this is what's going on, then the first obvious thing that you think about is that somehow there's an energy loss mechanism in the system. Right? You've produced an electron, it has to come out of the material, so somehow it's losing energy as it's trying to do that. And that was one good explanation. Curiously enough, that was refuted as a good explanation by experiment. Don't ask me how they did that, it's not very easy. It has to do with you being able to measure whether the material, in many, many quotes, heats up as the beta radiation is coming out, and that was not being observed. So let me make a brief pause to tell you of what was going on, say, in the 1920s as far as understanding nuclear physics. So first of all, let me remind you that nuclei were discovered, and we had this quote-unquote planetary model for atoms, which is very successful. So now the next job was to figure out how nuclei are formed. And here's the model of nuclear physics in the 1920s and 1930s. It's a great model, and it works very well. So you have a nucleus, and you say that the nucleus is made out of protons and electrons. Most of the mass comes from the protons, and the electrons are there to make the charge work out. So this is the model. And with this model, you can make a lot of predictions. So for example, helium-4 is 4 protons and 2 electrons. That works ridiculously well. But then people started running into other problems. One problem is very simple to understand. Here's nitrogen-14, which according to this model is made out of 14 protons and 7 electrons. Again, it's a good prediction. You get the mass right. But there's a big problem. It turns out that nitrogen-14 is experimentally determined to be a boson. This thing, whatever it is a fermion. It's not the same thing. So clearly there's something going on because you made a prediction that nitrogen-14 is a fermion, and you do experiments and it's a boson. That's a very big difference. There's actually another funny problem with this model, which is it has to do with magnetic moments. And people have started measuring magnetic moments, and they figured out that nuclei have magnetic moments as well. And you can quickly convince yourself, with everything that you know about magnetic moments today, that the electron magnetic moment is actually much bigger than the magnetic moment of nuclei. That sounds very puzzling because you're postulating that your nucleus is made out of a lot of electrons. And somehow the contribution of these electrons to your magnetic moment cancels out. Because otherwise you would expect the magnetic moment of your nucleus to be mostly of order the electron magnetic moment, and that turns out to be wrong. So these are all these problems that people were running into with our understanding of nuclear physics in the 1920s. And the solution to this, and this is the best thing people could come up with, is summarized here, is that people figured out, or they postulated, that these electrons that live inside of nuclei are just very, very weird. And you can say, no, nobody would say that. But of course, the smart people said that. And they took advantage of this. They say, hey, nuclear electrons are weird, and maybe that explains the beta radiation. Maybe they're so weird that they don't have to conserve energy and momentum, for example. This is a quote from Niels Bohr, and it says that maybe energy is not conserved in nuclear physics processes. And again, another thing which is important to keep in mind in this historical context is that this is a textbook on nuclear physics written by George Gamow in 1931, and it contains this sentence here. Gamow, by the way, was sort of a funny guy, so this is consistent. But he says that, blah, 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 this would mean that the idea of energy and its conservation fails in dealing with processes involving the emission and capture of nuclear electrons. This does not sound improbable if we remember all that has been said about peculiar properties of electrons in nuclei. So it was an interesting road that people were going down through, and all of that changed in 1930. And of course, this is a story that I assume 100% of you have heard before at least once, but I will tell you the story anyway because it's a great story. So the idea is that in 1930, Pauli postulated a different solution to all of these problems. And it was a very simple solution. So basically what he said was he had a solution that solved both a lot of the nuclear physics issues that people were concerned about, but it also solved this continuous beta ray spectra. And the story that's very well known is that this was actually not published as a paper. It wasn't even published as a proceedings in a conference, because this is a conference that Pauli didn't attend because he couldn't make it. But he actually sent a letter to the participants in the conference with his new idea, and he asked his friend to go to the conference and read it for him in the conference, which apparently is how it worked out back then. And this is a translation of Pauli's letter. It's a very short letter, so his friend didn't have to be embarrassed for very long. But this is a really interesting letter that has lots of interesting features to it. So he starts out by laying out what the problem is. He says, hey, we have this problem with the spin statistics theorem in a couple of nuclei that had been measured very well. Remember, this is Pauli. He invented the spin statistics theorem. So he cared about it very much, I suspect. And also this continuous beta spectra. So blah, 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 lots of things are going on. And he says, in order to solve all of these problems, I'm going to invent a new particle. So he invents a new particle, which he says also lives inside of the nucleus. And that particle better not have any charge, because those properties of nuclei were working very well, so we don't want to screw that up. So he called that particle a neutron. Now he also said, so he did some phenomenology. So I'm inventing a new particle. What properties must this particle have so that it fixes the problems that I'm trying to fix and hasn't been discovered yet? So that we do that all the time. That's sort of how we make a living nowadays. And so he said, so it has to be a spin-a-half particle, so it satisfies the exclusion principle. So if you add enough of these particles, you can choose whether things are going to be bosons or fermions. So that solves that problem. And you can solve the beta spectra in a very simple way if you say that the beta decay process is a three-body final state process. So the nucleus decays into another nucleus, an electron, and this neutron that comes out. And that explains why you have this continuum spectrum, because the electron is sharing all of this energy with this other particle that's coming out. And then he did a little bit of numerics to figure out how heavy must this thing be so that we've never seen it before. So he places an upper bound on the mass of this object. And then he also has to make some calculations about how come we've never seen this before. And that means that the penetrating particle, the penetrating properties of this object have to be very good. It has to be a very hard to measure particle. So that's basically all that he's doing over here in this first paragraph, is laying out the properties that this particle must have in order to solve all the problems and not be observed experimentally. Then here he has some concerns. So basically what he says is he's sort of ashamed that he's invented a particle that nobody could detect, and he doesn't like that. We've gotten past that. We can invent lots of particles that we can't detect, and we don't have any qualms about that. But then he has some funny sentences here about whether that's a good idea, and he's saying it's a good bet to take, and so on. And finally, he also explains why he can't go to the conference, because he had to go to a party, which is good. So that happened in 1932. And then lots of things happened right after that, which are very interesting. I'm sorry, this is in 1930. In 1932, in England, Chadwick, who was one of these renowned experimentalists who had done a lot of work, he actually discovered a new particle that was neutral. And he discovered it doesn't matter how. And he discovered this thing called the neutron, and that was a really big deal, because it changed the way that we do nuclear physics, for example. So right away, the information percolates throughout Europe, of course, because it was a very big discovery. And I probably won't tell the story exactly right, but the idea is then this got to Italy, and Fermi was talking to some people about the discovery of the neutron, and then somebody asked Fermi, hey, Chadwick just discovered this neutron. Is that the same particle that Pauli proposed? And then Fermi said, no, that has to be a totally different particle, because the particle that Pauli proposed is much, much lighter. So it's not a neutron, it's a small neutron, which in Italian is a neutrino. So Fermi did that, and that's the name that the particle that Pauli invented got. And if you know Italian, ino means small. It's a suffix that makes things small. Okay, so this is a small neutron to differentiate it from the big neutron. The name stuck, which is kind of interesting. It's also peculiar that this Italian suffix ino was hijacked by the SUSY people to indicate fermions. So you have Higgs-inos and charge-inos and gravitinos, and all these particles are, in quotes, little gravitons and little charged particles and so on, except that they could be very heavy. Anyway, I'm sure the Italians were not amused, but they've gotten used to it by now. So this is in 1932. In 1934, something much more important happened. Again, when the neutron was discovered, the nuclear model started to be revised. It became much more sane to say that nuclei were made out of protons and neutrons. So you didn't have to have any electrons or neutrinos inside of the nucleus. But then what Fermi did is he wrote down the Fermi Theory. And the Fermi Theory is an amazing idea that uses information that people had from other descriptions of physical phenomena. And basically what Fermi postulated was, he wrote down a theory for beta decay. And he said, we know how electromagnetism works. It's a current-current interaction. So if you want to do, say, electron-electron scattering, that's described as a current-current interaction. So I want to describe beta decay in the same way, except that I want to have some funny currents. And I want to postulate that you can have a proton-neutron current, and I can have an electron-neutrino current as well. And I don't know the nature of this current. It doesn't have to be a vector current. It could be an axial vector current, a pseudoscalar current, a scalar current, and so on. But he wrote down this theory here. And of course, this is proportional to some unknown constant, which is called a G, which we, of course, call the G Fermi. There's also a funny story here, if you've ever done calculations using Fermi theory, is that there are always some annoying factors of a square root of 2 or 2 floating around. I think that has to do with Fermi's definition of the constant, which is not optimal for doing calculations. Anyway, so he wrote down this theory, and this is an amazing idea that has lots of interesting consequences. Probably the most interesting consequence of this is that he allowed for the possibility of particles turning into other particles. We already knew about the fact that you could create, say, photons out of nothing, which is a really weird idea, but we got accustomed to that. This is the first time where you could have one kind of particle turning into another particle. So you could have a neutron turning into a proton, and then having an electron and a neutrino pair appear out of nowhere. And that was okay. So this was first written down here. And people, again, have grown accustomed to this. We, of course, don't even worry about that. But this is probably really, really weird. Because, this makes very little sense from the point of view of what does a particle mean, let's say. But the other thing that's very important is once you write down a theory that describes beta decay pretty well, you can fit the model to the, then you can actually calculate stuff. And one thing you could calculate was, so can we ever observe these neutrinos that come out? Because again, they do have some interaction. So it must be possible in principle to have these neutrinos come in and hit something. So you could calculate the cross-section for that. And for example, using a modern language, you could have the neutrino hit a proton, produce a positron and a neutron. That's possible. Of course, you calculated the cross-section, and the cross-section was just ridiculously small. By the way, one thing that Pauli had said was that it was never going to happen that this neutrino would be discovered. He actually had some bets on that, which he lost after about 20 years. But nonetheless, he was probably very happy about that. Anyway, so now we had a model that told us how the neutrinos interact, and that allowed us to contemplate doing experiments. Again, in 1934, when this theory was written down, the safe conclusion was that it was not going to be possible to do an experiment ever to see a neutrino. That was a good assessment at the time. So let me pause here for a second and tell you about other stuff that was going on. Again, particle physics is a really exciting field in the 20th century because we knew very little and we were discovering all these funny things. By the way, there's one thing which I won't talk about, which is this interaction here is the interaction that we write down today as an effective theory for describing neutron decay. It works pretty well. This current here, certainly written out in this electron-neutrino part, that's the V minus A current. That's characteristic of the weak interaction that violates parity maximally. So you've all heard about this. So this theory is written down in 1934. It took until the late 50s for people to figure out experimentally what this current was. There's lots of debates, lots of fights, and every once in a while the data looked like it was I can't remember, scalar and tensor theory. Half the time it looked like a V minus A theory or a vector theory or an axial theory. There's a lot of fun history that's going on over here. And ultimately, this was resolved by better experimental data. But then there are also some very famous people who wrote theory papers addressing the nature of this current, and eventually it was established that it's a V minus A current. One of these papers is by Feynman and Gell-Mann. I think that's the only paper that they wrote together. And the story is that they actually did separate papers, and somebody in their department convinced them or made them actually write just one paper. That story might be false as well, but it sounds like it's a good story. So I've heard this more than once, so it must be true. Okay, so what else is going on? People were trying to understand how neutrons and protons stick together. The most successful model for that at the time was postulated by Yukawa. This is the Yukawa model that postulated the existence of a new particle, which is called a meson. I don't know what name he gave it at the time. I think it was the meson, but that doesn't sound right. Maybe that's right. Okay, I think it's the meson. And I'll come back and I'll remind you what that name means. So people know why it's called a meson, right? What's that? Yeah, so the mass is somewhere in between the electron mass and the proton mass, which of course makes no sense for B mesons, but that's a different story. But yeah, but that's where this name comes from. And what's interesting is he wrote down in 1935, and he made a calculation for the mass of that particle, which is about 100 MeV. This is in 1935. 1 year after that, they discovered a new particle doing cosmic ray experiments in 1936. And that particle had a mass of about 100 MeV. And people got really excited about that because they had just discovered Yukawa's meson, which is great, except that it was wrong. And people figured out that it was wrong because the properties of this particle had absolutely nothing to do with the properties of the meson that Yukawa had postulated. But it was very, very confusing. And it took about a decade for somebody to figure out or to postulate that actually what happened was these experiments were happening in a way that the Yukawa particle was being produced. This is happening in cosmic ray experiments. But then that particle was decaying into some other particle. And using modern language, the Yukawa meson is called a pion, and that's the pion that we know about. And the thing that it decays into is a muon. And the muon is the thing that you actually detect in the experiments. This was actually confirmed later on, both in cosmic ray experiments, when people decided to put cosmic ray experiments way up high in the atmosphere. So they did experiments high in mountains and things like that. And also when people started inventing particle accelerators. And they could produce pions directly in the laboratory. And they got very good at detecting them. So there's a lot of history there as well. So this particle that was discovered in the 1930s was the muon. The muon is a very weird particle. The muon is the particle that after it was established what the muon was, that invited the question, who ordered that? And that was the first second generation particle that we ever discovered. So we've talked about that. So now that we know where we are, so we've discovered muons. And now we want to talk about how did people actually measure the neutrino. So remember, in the 1930s, people did a calculation to figure out what the cross-section for detecting a neutrino was. And they concluded correctly that it was impossible to do an experiment that would actually allow you to observe a neutrino. And between the 1930s and the 1950s, something very important happened. Actually, lots of very important things happened. There was a big war. And people invented nuclear weapons. And they also invented nuclear reactors. For the same reason, by the way. Those three things are highly correlated. And the neutrino was actually discovered in an experiment by Reines and Kao, taking advantage of nuclear reactors. Now, nuclear reactors are very important because they happen to be, you're basically taking a beta decaying nucleus and you're collecting lots and lots and lots of them in one place. So you get a very strong source of neutrinos. So even though the cross-section didn't change, what changed was the fact that you could now get a lot of these neutrinos to actually do the experiment. One thing which I always like to point out is that this was not Reines and Kao's original idea. They actually had a different idea to detect the neutrinos first, which was not funded. This is a great idea. So this is their neutrino experiment. And there's another physics process that releases a lot of neutrinos at the same time. And that's a nuclear explosion. People knew how to do that. And they also had lots of those going on in tests of nuclear weapons. So it wasn't totally crazy because this was going to happen. So this is the proposed experiment. Your bomb is exploding over here. and then you put your detector over here. And then you try to detect the neutrinos, and I'll talk about how you do that. Now, there's some technical difficulties. The biggest one is that you will have your detector here, and you want to turn on your detector while a bomb is going off right next to it. That's a very difficult experiment. Their solution that's presented here, this is from their proposal, is what they were going to do is, when the bomb went off, they would let the detector fall. And that's a great idea, because then when the ground is shaking, the detector's just fine. It's falling, but it's fine. And then they have here feathers and foam rubber, which hopefully will hold the detector and everything will be fine. And so this is a great proposal. It was encouraged, but it was not funded in the end. By the way, the flux of neutrinos that comes out is quite large. The experiment in principle could have worked. The only other fun thing is that there's the distance between the explosion and the tank is 137 feet. And that's either a joke or it's just an amazing coincidence. But anyway, so that's that proposal. What's that? Oh, maybe. I mean, I think we still propose very amazing experiments, I think. I would like to argue with that. Not that amazing, yeah. I don't know if anybody ever measured the neutrino flux from a nuclear explosion ever. Something to be thought about. Okay, so this is a really cool experiment, and we still do the experiment exactly the same way for neutrinos that come from nuclear reactors. The idea is very simple. You're looking for this reaction that you could calculate with Fermi theory. So a neutrino comes in, hits a proton, produces a positron and a neutron. And what people figured out was, so if you build a big experiment, this positron that comes out will annihilate with some electron in the material and will give you a gamma ray signature, so you see photons out of that. So that's great. That's one thing that you look for is photons in your detector. The problem is there are lots of other junk that will do exactly the same thing, will produce photons in your detector. So what they figured out was, hey, there's also this neutron that comes out. So if I could tag the neutron, because the neutron, it random walks around until it gets captured by a nucleus, and then the nucleus de-excites. So if you have a large cross-section for nuclei being absorbed, neutrons being absorbed, you could see photons coming from this de-excitation of whatever absorbed the neutron. And if you do that, then you can first see a big burst from the positron, and then some calculable amount of time later, you see another burst of photons coming from the neutron capture. And that was a great way of getting rid of backgrounds, and it's still a great way of doing these types of experiments. So these coincidence measurements are very important for doing reactor neutrino experiments, and we still use them today. Okay, so they've discovered the neutrino in 1956, and again, by discover it means that they managed to see a neutrino hit something. Again, if you're a purist or if you're a theorist, then you can argue that the neutrino was discovered by Pauli in 1930 to explain beta decay. But that's kind of a cheat. We had to see it just to make sure that it was the real particle. Then a lot of progress happens after that. In 1958, we figured out that neutrinos are completely left-handed. The helicity of the neutrino was measured. So neutrinos are left-handed, antineutrinos are right-handed. This is a really nice experiment done by Goldhaber et al., where they figured out that even though you can't see the neutrino, you can still infer from angular momentum conservation of a complicated nuclear physics process what the helicity of the neutrino is. And of course, it's a maximally parity-violating interaction. Okay, so we're here in 1958, and I don't have a lot of this story written down, so I'll tell you about it in words. Remember, we discovered this thing called the muon. And the muon is an interesting particle. We figured out that it decays into an electron and two neutrinos. That's by far the dominant decay mode of the muon. Otherwise, the properties of the muons are very electron-like. That's why it's called a second-generation particle. It's a partner of the electron. Then people started asking questions about the muon. And one really good question you can ask And they asked that question at lots of different levels. If the muon looks like an electron, it's very similar to what happens with radioactive nuclei, in the sense that we can take a nucleus and we can convert it into, in quotes, a heavier version of the same nucleus by exciting it. And then those nuclei tend to de-excite by emitting gamma radiation. So people are starting asking the question, maybe the muon is an excited state of the electron. It's a very good hypothesis. So that means we should be able to observe this excited electron de-exciting into an electron and a photon. So people asked, does this thing happen? And they started doing experiments. And it turns out it doesn't happen at the 10 to the minus 1 level if you talk about branching ratio. Doesn't happen at the 10 to the minus 2 level. So at some point people said, yeah, this excited electron thing is just wrong. However, they went back to asking this question again because they had another idea, which was, so we know how this muon decays, right? The muon decays. So let me write it down over here. So the muon decays into an electron, a neutrino, and an antineutrino. So that's the dominant decay mode of the muon. And we know that works really well. It's also described by the Fermi Theory, which is a sign that the weak interactions were the same that describe muon decay and pion decay and nuclear beta decay. But if this is how the muon decays, people knew enough about perturbation theory back then in the 1940s that you could ask yourself, why don't I close this neutrino loop like this and add a photon somewhere? So the muon has to decay into E gamma. It's a simple calculation. It wasn't simple back then. People made some estimates. And the estimate was that the branching ratio was something like 10 to the minus 4. Or 10 to the minus 5. The error bars were big. So again, people kept doing experiments. And they got to 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. And the branching ratio was smaller than that. So this is a big puzzle, because the muon definitely can decay into electron, neutrino, and antineutrino. But somehow, something is preventing it from decaying into E gamma. This was a big puzzle, and this was actually resolved in a way that's very important. So in the language of the day, the solution to this was called the second neutrino hypothesis. The idea was that when the muon decays into an electron, a neutrino, and an antineutrino, then the neutrino and antineutrino that come out are not a particle-antiparticle pair. They're two different particles. So this is a second neutrino hypothesis. And along with that, we could explain, using more modern language, that the muon doesn't decay to E gamma because it violates a conservation law. So we invent a new quantum number. There's an electron nest and a muon nest. And the electron nest and muon nest are conserved. We call that electron number and muon number. And that explains why mu to E gamma doesn't happen. This is important because this conservation law is actually wrong. We've established that experimentally by now. But nonetheless, this two neutrino hypothesis came up, and the question is, how do you resolve that experimentally? And people came up with a way of doing that. This is in the 1960s. This is an experiment that discovered the muon neutrino, if you want to think about it that way. It's a very important experiment. It's actually peculiar that the discovery of the second neutrino got the Nobel Prize before the discovery of the first neutrino, but that's how Nobel Prizes work. So again, there's this very famous experiment, and the biggest contribution of this experiment is that these people, this was led by Letterman, Steinberger, and Schwartz at Brookhaven, they actually produced the first neutrino beam. The idea is really simple. So you take protons, you shoot it on a target, a bunch of pions come out. If you wait long enough, the pions decay. Pions decay into muons and neutrinos. If you wait some more and you put a bunch of junk in front of the beam, all of the muons get absorbed, and what you're left with are only the neutrinos. It's a really crappy beam. It's very, very big. It's a big beam like this. And you can't not have a very big beam because you're basically taking a bunch of pions that go everywhere and you're just very, very quickly trying to aim them all going in the same direction, and then you wait, and of course when the pions decay, the muon and the neutrino go all over the place. But it's a beam nonetheless. This is still how we make neutrino beams today. We haven't gotten any smarter. And the idea is very simple. If you take these neutrinos, and if you believe in this muon number conservation law, these have to be muon neutrinos. So that means if you take these neutrinos and you make them hit something, they should only be able to produce muons, and they should not know how to produce electrons, right? Because if this particle is a muon neutrino, this reaction goes, but this reaction is forbidden because it violates both electron number and muon number. So that's the experiment that they did, and that's what they confirmed, is that, and just to keep in mind, if this neutrino could do both things, it would probably make more electrons because the electron is lighter. So there's more phase space for that. So they do the experiment, and sure enough, this never happens, and this thing here always happens. What's also interesting about this is that the neutrino experiments we do today are actually aimed at measuring exactly this thing that never happens. But we know how to make it happen if we're very patient. So this is the experiment that established that there's actually a second neutrino. Then, of course, in the 1970s, people found out that there's another particle called the tau, which is also like an electron and a muon, but it's even heavier. So it stands to reason that there's a third neutrino. The presence of the third neutrino was established in lots of different ways, including at LEP from Z decays. But it took us a really long time to actually see the tau neutrino do something. So again, just like we wanted to see the muon neutrino do something, and we wanted to see the electron neutrino do something, we wanted to see the tau neutrino hit something and produce a tau. This experiment was successful only in the 21st century. So there's this thing called the donut experiment, which took place at Fermilab. This is a great experiment name. It stands for Direct Observation of New Tau. And this is done in 2001. One thing which is fun to keep in mind, this is way after the top quark was discovered. So again, if you're a skeptic, the tau neutrino was the last matter particle to be discovered in the Standard Model. By a lot. I mean, the top is in the mid-1990s. Let me show you how the tau neutrino is discovered, because it's kind of cool. So this is how you see the tau neutrino. What happens is you try to make a tau neutrino beam. You do it in exactly the same way that you produce this muon neutrino beam, except that the pion doesn't decay into tau neutrinos. So you need a heavier meson for that. So you need a higher energy beam that produces a lot of D sub S's. These are C bar S bound states which like to decay into taus and tau neutrinos. So if you have a high enough proton hitting a target, you produce these charmed and bottom mesons, and these guys can decay into taus, and then you get your tau neutrino beam. So the idea is, this neutrino is coming from over here, you don't see it, it hits something, it produces a particle that travels a little bit, and then it has a kink in it, and that's indicative of a tau decay. So the idea is that a tau was produced over here, and then it decayed into a muon and two neutrinos, which is why you get this kinematical kink. This is a challenging experiment because this happens relatively quickly. I think the scale here is of order a fraction of a millimeter. That's what's written down over here. And on top of that, this has to be a neutrino detector. The cross sections are still very small, so that means you need a lot of mass. So you need a really dense detector with a lot of mass in it, which makes measurements really hard, because if your detector is really dense and massive, that's great because lots of neutrinos will hit it. That's bad because everything that gets produced will be absorbed by your detector. So that's why people were clever enough to have a technology where you actually could see the tau track that was produced inside of this thing, which I think was lead. Okay, so you have this lead emotion detector. The lead gives you the target. The emotion gives you the ability to see these tracks. And it's a very big detector. And this is a picture of almost all of the tau neutrinos we've ever seen ever. Really, ever. The number of tau neutrinos we've ever seen is less than 10. That's less than the sample of Higgs bosons that we've accumulated from the collider experiments. We don't know a lot about the tau neutrino if you don't believe in the standard model of weak interactions. We have not measured its properties at all. The final thing I'd like to mention about this experiment is that this experiment is crazy hard. Because remember, we're producing this tau neutrino beam, which is really hard to do, and it's really inefficient. Because every time you produce a d sub s meson, you produce a gazillion pions, which are happy to decay into muon neutrinos, and kaons, which also decay into muons and electron neutrinos. So when they do the experiment, and they show us these really, really nice looking curves, what they actually see, and by the way, to make it worse, this is not a real time experiment. This is an old-fashioned experiment where the tracks are left in place and you have to go look for them later. So their sample, already a little bit cleaned up, looks like this. These are all the tracks that they have. And out of this mess, you have to figure out that there's a tau decay in here. And they tell us that they know how to do it. And we believe them. And that's why we know the tau neutrino was discovered. All tau neutrino observations, by the way, that were done and were identified as tau neutrinos come from these types of experiments. The other evidence that we have for tau neutrinos is indirect by looking at neutral current events in large atmospheric neutrino detectors and inferring from the absence of muon neutrinos that the tau neutrinos are the thing that are doing something. Okay, so good. I think I made good progress. So let me summarize the story so far. So if you pick a standard model textbook from the 1980s or the 1990s, it will have a really tiny chapter on neutrinos, and that's what that chapter will say, if it's a long one. This is what we know about neutrinos. There are three flavors of neutrinos: an electron neutrino, a muon neutrino, and a tau neutrino. And they're defined according to what's the charged lepton that talks to it via charge current weak interaction. So the nu E always comes in with an electron, and every time it hits something, it only knows how to produce electrons. There's a nu mu, and then there's a nu tau. They only have weak interactions, so they only talk to the W and the Z. We have no evidence that that statement is incorrect. As far as we could measure until very recently, the neutrinos were supposed to have no mass. And if this had been true, it would still be quite interesting. So the neutrino was the only massless fermion that we knew about. And of course, we were wrong, so we don't know about that either. But massless fermions are very interesting. And you all know about biofermions. So a massless neutrino is the poster child of biofermions, especially because it's only produced by weak interactions. And the weak interactions are maximally parity violating, which means that every time you do an experiment with neutrinos, the neutrinos are always left-handed. Every time we do an experiment with antineutrinos, the antineutrinos are always right-handed. We have never seen that not be true. And that's interesting. So that means we can classify the neutrinos by their handedness. That's what's written over here. And then there's this thing which I just said. The neutrinos are a great Weyl field. As far as we know, we only need 2 degrees of freedom to describe a massless neutrino. The left-handed guy and the right-handed guy. And that's exactly what a Weyl fermion contains. Okay? And this is important because we have to check if that statement is actually true or not. Finally, there's on top of this flavor conservation law, there's another conservation law called overall lepton number conservation, which is if you do an experiment and you count how many leptons go in, the number of leptons that go out is the same. And it's in this sense that we can define a neutrino versus an antineutrino. And again, as far as we know, this is an absolute true statement about nature. Okay, so now the next step is for me to tell you why a lot of the information here is wrong. And this has to do with stuff that started happening in the 1960s. And I'll start telling you this story, and I have 15 minutes more, unless I don't understand half an hour more. Oh, I have a lot of time, so you're in trouble. Okay. But we have lunch at some point. Although I should ask, do people have any questions? Yeah. Yeah.
For that tau neutrino experiment, how do they distinguish the lines? Which lines were the real signal from the noise?
Oh, here? So all the lines are signal. They're all due to other neutrinos that are going through the detector as well.
Right.
And they just have a very, very good reconstruction algorithms. That means that they are really good at reconstructing the line and then getting rid of it. There are more things you can do. What they really look for are muons. So this is all about muons. And for example, in more modern detectors, what they will do is they will have a muon detector in the back, and then they will say, do I get a muon in my muon detector? If that's true, let me follow it back through this emotion detector and reconstruct that, and that will tell me which are the tracks I care about. And that helps a lot. And then, of course, you have all discontinuous tracks. You throw those out because those are other weird stuff that's going on. And eventually, they have this algorithm to solve this. There's a technological problem, which is how do you do this in practice? One way to do it is you hire a bunch of people, and you make them do it for you. And that's how you did it until very recently. The big technological change was to teach the computer to do it efficiently and fast. And so effectively, efficiently, and quickly. And they've developed these automated emotion scanning techniques that allow these experiments to actually exist in an even worse environment than this one. But yeah, it's an engineering marvel that this experiment works at all. And it works, and I think people are convinced of that. And we don't have any new experiments that are out there that use this kind of technology. But people always wonder about whether we could do that. And in particular, every time we talk about detecting taus, it's a big challenge because the tau is a very annoying particle to detect in a neutrino experiment because it doesn't look special. So you produce a tau, it decays really quickly, either into muon or an electron. That's boring because the muon and the electron neutrino do this by themselves. They don't need a tau in the middle. Or they decay into pions and such, which is good because that's different, but that looks a lot like a neutral current process, where a neutrino comes in, hits a nucleus, and emits a bunch of pions. So we don't have any good way of distinguishing other known phenomena from taus, except for the fact that this tau lives a little bit and then decays, so you get this kink, but the kink is too small for you to resolve with other types of experiments. And the other issue you can do is you can try to do it kinematically in a statistical basis. And the idea is the following. People tried this in the NOMAD experiment at CERN when they were looking for neutrino oscillations at much higher delta M squares. The idea is the tau neutrino would come in, it produces a tau, and then the tau decays to a muon. Now, the way that could look different from a muon neutrino coming in and producing a muon is that if you follow this tau path, the transverse momentum of the muon can be much bigger because you're producing a tau, and the muon can get a big kick in the perpendicular direction to the beam, and you can't do that just by producing a muon because of energy momentum conservation. So by looking for high PT events, you could get a sample which would have been enriched by the tau neutrinos. They didn't see anything, by the way, but that was the plan for that experiment. So statistically, there's some good ideas. If you care about hadronic tau decays, the tau really likes to decay into rho mesons because of this thing called the vector meson dominance. So that's one other handle you have. If for some reason you get an enrichment of rho mesons in your neutral current sample, that might be a signature that you have more taus there than you have other kinds of neutrinos and so on. But it's still a challenge. We're not good at detecting taus. We're really good at collider experiments, or we're pretty good at collider experiments, but that's a totally different world. Collider experiments are really nice, and you can see these beautiful, they're called the tau jets, that look exactly like a tau is supposed to look, as opposed to a pion or something that hadronizes in some messy way. So, other questions? Okay, so let me start telling you about neutrino puzzles, and that's the story which changed everything. And the idea is that people have figured out by doing experiments that if you produce a neutrino and you wait long enough before you detect it, it can actually change flavor in flight. That's what we figured out by doing experiments. And the evidence for this is absolutely overwhelming. We have done experiments with different neutrino sources, and we've done experiments with different neutrino energies, and we've done experiments with different we actually don't wait time. We just let the neutrinos travel a really long distance. So this also changes the function of distance. So the evidence for this is really strong, and that's what changed the way that we understand neutrinos. And I want to start telling you about this by talking about the solar neutrino problem. It's a very old problem. It's very important to remember that the Institute played a huge role in understanding solar neutrinos. This is, the work of John Bacall, who was a big nuclear theorist, was done almost all of it here. And he was somebody who set out to try to understand how the sun works. And the sun works, as you know, by nuclear reactions. So there's a lot of temperature, pressure, and so on. And people figured out that this is what's going on in the sun all of the time. And this is what you'll learn in grade school or whenever it is you learn about this, hopefully high school. So the sun shines by proton fusion. So there's enough protons there and enough heat to make two protons ultimately combine into helium-4. So you're taking two protons. This happens through a series of steps. And all that we care about is that, so it starts out with proton-proton going into deuteron, plus a positron, plus an electron neutrino. Some of the time you have this funny proton-electron-proton initial state going into deuteron plus an electron neutrino. And then higher up the chain, you produce other nuclei like, say, beryllium-7, which electron captures and produces lithium-7 plus an electron neutrino. And then you also produce boron-8. Boron-8 is a highly unstable nucleus. Boron-8 decays into beryllium-8, which is again highly unstable, but that part we don't care about, and then a positron and an electron neutrino. And the main point is, throughout this entire process, you are producing a lot of electron neutrinos. By the way, they're not electron antineutrinos, they're electron neutrinos, and that's easy to understand because the sun is proton rich. So mostly what the sun is doing is converting protons into neutrons by fusion. And when you do that, you emit a lot of electron neutrinos, not antineutrinos. Beta decay is the other way around. You normally have a nucleus that's neutron rich, so you're converting neutrons into protons, and then you're emitting antineutrinos. So this is the idea. We can calculate this, and by looking at the properties of the sun, we can figure out how many neutrinos come out as a function of energy. And the reason I'm talking about this is that nobody talks about this anymore. It's kind of old history, but it was not the case 20 years ago. It was very important. So this is how the sun works. So this is neutrino flux as a function of neutrino energy. The neutrinos are produced in those different nuclear reactions that I showed in the previous slide. And you notice that most of the neutrinos come out from pp fusion. They don't have a lot of energy. The energy is measured in MeV. Their energies are below, say, 400 keV or so. But the flux is gigantic. There are no units here, but it's big. So just look at it that way. This is a very old plot. This plot has evolved a little bit, but only very, very little. It has a lot of information. But this is the flux of neutrinos coming from the sun. And this was calculated in the 1950s and 1960s. And people started asking themselves, how do I measure this? Can I measure this at the Earth? And the answer is, the flux is really, really large. So that's good. The flux is billions of, the famous outreach numbers are, trillions of neutrinos go through your body every second. So that's a big flux. That's a good start. So people started figuring out, how do we measure this? And I don't remember what my next slide says. Okay, so the first kinds of experiments that came out, and again with a large influence from John Bacall, are these chlorine experiments. And the idea for measuring these neutrinos is very simple. You take something that, and you kind of do an inverse beta decay in it. Remember, beta decay is a nucleus emits an electron. A nucleus emits an electron and an antineutrino. If you flip the leg, which I can draw here. So this is normal beta decay. So I can do this reaction here. So it's a simple idea. So you want to look for, so you want to look for an electron neutrino hitting a nucleus and producing an electron. So your signature is an electron. And of course, you want to do this with a material that doesn't undergo beta decay by itself. And again, this will become important later, because if this undergoes beta decay by itself, you're in trouble because you have all these beta decays happening inside of your experiment at the same time. And this is what people set out to do. And actually, the first two experiments, this is this chlorine experiment, they decided to do something different, which is instead of looking for the electron, you looked for the nucleus that you're producing. So the idea for the experiment is very simple. You take a lot of chlorine, you put it deep underground when you're very far away from cosmic rays and other radiation and stuff, and then you wait for a solar neutrino to come in and convert a chlorine nucleus into argon, it turns out. Argon is great because it's a noble gas. That means that if you produce argon inside of your big chlorine tank, it's just going to sit there. And then you wait a long time for this to happen enough, and then you take your big vat of chlorine, and then you look at it, and then you see how much argon you have produced. That's the plan. It's a totally crazy plan, because the amount of chlorine that you need is gigantic. That's where we get into this era of experiments that have masses measured in kilotons. Okay, so it's a big, big vat of chlorine, which was taken to a gold mine in Homestake, South Dakota. And the signal that you're looking for is really small. Again, what they would do is that they would expose the chlorine for about a month. They would take it out, and they would look for something like tens of argon atoms inside of this big vat of chlorine. That's the experiment. It's a very difficult experiment. It involves a lot of chemistry, which makes it very, very hard. And somehow people did it. So they actually managed to do the experiment, and they managed to see these argon atoms, and they've established that they can see neutrinos coming from the sun. That's a Nobel Prize winning experiment, by the way, just for seeing the neutrinos coming from the sun to Ray Davis. This is the chlorine experiment. And this experiment was a great success, except for the fact that we knew how many neutrinos we were supposed to get, and they were off by about a factor of 3. So they saw a factor of 3 less neutrinos coming from the sun than they expected. This is in the 1960s. And of course, when this result came out, and I don't know because I wasn't there, but I can predict that what happened was people said, great, we know neutrinos are coming from the sun, this is a great measurement. It's off by a factor of 3, but who cares? I mean, it's a really hard calculation because you have to understand how the sun works in detail, and you're doing this crazy experiment where you're counting atoms in this gigantic vat of chlorine. By the way, chlorine is like cleaning fluid. It's not very sophisticated. So the fact that you're off by a factor of 3, factor of 3, that's not so bad. This is in the 1960s. The experiment continued for many, many decades. I mean, the experiment stopped running in the early 2000s. And they confirmed this factor of 3. The calculations were refined. There's a lot of criticism of how the calculations were done. Maybe these models for the sun were just wrong in some interesting way, and so on. So in order to resolve that, people built a different kind of experiment. These are gallium experiments. It's exactly the same idea, a large volume of gallium that's converting into germanium. And then there's some clever technique of identifying how much germanium you've produced. And the idea is, I should have said this, the argon that you produce is radioactive. That's good because you can see the radioactivity coming from that. The same is true of the germanium that you produce. That's kind of how you see these atoms. So this gallium experiment was also done, and the nice thing about the gallium experiment, which I didn't explain, so these lines here show the threshold of the experiment. In the case of the chlorine experiment, if the neutrino has less energy than that, then the reaction doesn't go. It's not kinematically allowed. With the gallium experiments, it's the same. It has a threshold, but the threshold is a lot smaller. And this was very important because with the gallium experiments, you could see this gigantic pp neutrino flux. So that's why these experiments were built for, was to check whether the result of the chlorine experiment was correct. And they were also sensitive to the PP neutrinos, and they were sensitive to the PP neutrinos. Sure enough, when they do these experiments, they also see fewer neutrinos than they anticipate, by a factor of 2. Finally, at around the same time that the gallium experiments were coming on, we had these really big water tanks that were built underground to look for proton decay. And somebody figured out, hey, we can do solar neutrinos with that. It has a much higher threshold. It works on water, and what you're basically seeing is electron scattering on the electrons in the medium. And you can convince yourself of why that's true. First of all, electron neutrinos don't know how to do charge current scattering off of protons. It just doesn't work at low energies. It's not possible. So if you don't believe me, just try. You'll see that you violate Lepton number if you try to do that. Or you have to produce a delta plus plus resonance, which takes a lot of energy, so you can't do that. And electron neutrinos can't really interact with oxygen either, because the oxygen is a very, very tightly bound nucleus. It's a doubly magic nucleus, if you remember what that means. If you don't know what that means, you should look it up. But oxygen is doubly magic. So they have to talk to the electrons. And again, this large water Cherenkov experiments also see a big depletion of the flux. So don't look at the last part of the plot. This is a colorful plot, and all you want to take from this is the blue lines are the measurements of the neutrino flux in some weird units. In case you like ancient history, these were measured in a SNUs. These are solar neutrino units. So the flux for the chlorine experiment was 7.6 SNUs. This is true, by the way, I'm not making this up. And the measurement is 2.56 same units. So this is the chlorine experiment. This is the water experiments. They expected this much, and they got half. These are the gallium experiments. They expected this much, and they also got half. What the colors here indicate is where the neutrinos are coming from that contribute to this particular flux. So the boromate neutrinos are this neutrinos over here from boromate decays. The PP neutrinos are these guys. And then you have these lines, which are mostly beryllium-7. So you notice that all of these experiments see a big depletion of the number of neutrinos that you expect. And in order to resolve this problem, we had to build a new experiment that made measurements that look like this. And I'm not going to talk about this today, but I'll start talking about this tomorrow. This is the SNO experiment that actually solved the problem for us. But this is where we were at the end of the 1990s. And I'm not going to talk about the SNO experiment now, but since I'm trying to do some time management here, the other puzzle that people ran into was with neutrinos produced in the atmosphere. This is important because we still care about these neutrinos today. And the idea is very simple. There are cosmic rays hitting the atmosphere all the time. People learned that more than 100 years ago. And these cosmic rays, when they hit the atmosphere, they produce particles, mostly pions. Pions and kaons, a little bit of charm. People do research on that. But if you produce a lot of pions, then the pions will decay, and the pions decay mostly into muon neutrinos. That's what we care about. Now, the muons that are also produced in pion decay will also decay some of the time, and they decay into, again, muon antineutrinos, electron neutrinos, and electrons. So you have a flux of neutrinos coming all the time, bombarding the Earth. So that's the atmospheric neutrinos. And they have lots of nice properties. One really nice property is the following. That's what's depicted here in this picture. Is if you put a detector underground, we should be so lucky we could go this deep. But if you put a detector underground and you ask, how many muon neutrinos do you get from some solid angle on top of you? And then you compare with how many neutrinos you get from some solid the same solid angle in the opposite direction. So you look at the neutrinos coming from above, and you look at the neutrinos coming from below. You can convince yourself very quickly, using the fact that we live in 3 dimensions, that the number of neutrinos that come from below in the same solid angle is the same as the number of neutrinos that you should get from above. That's a very, very simple prediction that you can make that only depends on geometry, and it only depends on the fact that the number of neutrinos that gets absorbed by the Earth is ridiculously small. So you can neglect that. So if you believe in those two things, which only rely on geometry and the weak interactions being very weak, then you expect the number of neutrinos that come from above to be exactly the same as the number of neutrinos that comes from below. That's a very, very simple prediction. So you wanted to measure one. And one manifestation of this experiment is a Super-Kamiokande experiment. They measured this ratio and they got a half with a very small error bar. So they find out that the number of neutrinos coming from below is actually about a half of the number of neutrinos that are coming from above. Now, from a historical point of view, it's interesting to think about these experiments. And like I said, the first generation of this in Japan is the Kamiokande experiment. There was also an experiment in the US called the IMB experiment. And these were not neutrino experiments. These are proton decay experiments. Okay, and if you don't know this, I'm sure you've heard about Super-Kamiokande. And you might have asked yourself, what does this mean? And you probably said, oh, I don't know what it means because I don't know Japanese, for example. But what it means is a Kamioka is the name of a mine and also a town that's right next to it. The name of the mountain, I think. I could be saying this wrong, so don't quote me. It's the name of either the town or the mountain or something in between. And then this NDE stands for Nucleon Decay Experiment. So this is a Nucleon Decay Experiment in the Kamioka mine. Now, why were they caring about this? Now, the reason they were making this measurement was they were looking for proton decay. So you put your experiment deep underground to run away from backgrounds. But there's one background you can't run away from, which is neutrinos. So these neutrinos producing from the atmosphere are the background for proton decay experiments. So of course, if you have a background in your experiment, you want to measure your background really well so you can get rid of it and understand it and so on. So the atmospheric neutrinos are a background for proton decay, and they led to this amazing discovery. Some skeptics will say that the discovery of atmospheric neutrinos is the biggest contribution of grand unified theories to date. Because grand unified theories were the things that allowed you to predict the rate for proton decay. And if you believed in those theories, you could make a prediction, and that told you what kind of experiment you should build. And you build the experiment, you go out to measure a background, and then you discover that neutrinos change flavor. That's nice. I have to show you that they have done a much better job than I've just explained, because they can measure both muon neutrinos and they can measure electron neutrinos. They can also measure the neutrino energy at some level, so they take their sample and they split it up into electron neutrinos and muon neutrinos. They split it up into muon neutrinos with a lot of energy, muon neutrinos with not a lot of energy, and that's what all of these plots here represent. And this here is the number of events that they get as a function of the direction where the neutrino is coming from. And this is cosine of theta. So cosine of theta of 1, these are neutrinos coming from above. And cosine theta of -1 is neutrinos coming from below. And you see that there are lots of points. The points are data points. What changes between the panels is these are the electron neutrino candidates. These are all muon neutrino candidates. That's not true. These are muon neutrino candidates, muon neutrino candidates. These are more complicated muon neutrino candidates. Oh no, these are all muon neutrinos with higher energy. So this is low energy muon neutrinos, higher energy muon neutrinos, highest energy muon neutrinos. Okay? So if you look at this plot, you also see some lines. The solid line is what you expect from our understanding of cosmic rays. And you see that there's some structure here, which is kind of exciting, that has to do with the Earth's magnetic field and how the cosmic rays are coming in and so on. But you notice that the data points tend to deviate a lot from what you expect from your Monte Carlo, except here, but I'll come back to this later. So you see that the data points are very, very poorly described by the Monte Carlo. And you notice lots of features here. One is neutrinos that are coming from above are behaving more or less in the way that you expect. Neutrinos that are coming from the other side of the Earth are not. Electron neutrinos are fine. The electron neutrinos are not doing anything. So it seems that there's something going on with the muon neutrinos. And this result by itself, by the way, this is a Nobel Prize winning experiment because of mostly this plot. This is a more modern version of the plot, but this is from 2004, I guess. So it's not so modern. But this is a really, really exciting plot because just by staring at this plot, you can convince yourself that neutrinos must have mass. Okay, you don't have to know anything. You just have to believe in Lorentz invariance. There's one caveat to this, which I'll mention in just a second. And the reason is very simple. So if you stare at this plot here, it tells you that neutrinos that come and travel a short distance behave differently from neutrinos that travel a really long distance. The reason this is very exciting is that it tells you that somehow neutrinos can tell time. They can tell whether they have traveled a short distance before being destroyed or whether they traveled a long distance before being destroyed. Now, massless particles don't know how to tell time. Massless particles live a really intense life where everything happens at once. Okay? Massive particles can tell time, and it indicates very, very clearly that the neutrinos can tell time. They know when they've only traveled a little bit versus when they've traveled a very, very long distance. Okay, so this is a very, very big deal. The only caveat to this, of course, is that if somehow the neutrinos were being absorbed by the Earth in a way that we don't know how to describe, then that could lead to an effect that also looks like that. So you have to believe in the weak interactions or that neutrinos don't have very, very strong interactions. By the way, if you watch the movie 2012, where the Earth, something bad happens, the reason for that was that the sun started producing more neutrinos than it was supposed to. And then all hell broke loose. So these people probably know that neutrino interactions in the core of the Earth are very, very strong. And that might be the reason for these data. But anyway, the other way that this is violated, by the way, is if you violate Lorentz invariance. So inferences about proper time and so on, they only exist in the context of Lorentz invariance being a good symmetry. So if you violate Lorentz invariance, then all bets are off. Then you can do whatever you want. All right. So I think I'm going to stop. Well, so let me say, do people have any questions? Yeah.
Is there any reason for the factor of 2 between the ones coming from the top or below, or just coincidence?
It's a coincidence that it's a factor of 2, but this factor of 2 informs you about new neutrino parameters. So that means that whatever you do to change neutrino properties, you have to explain this factor of 2. Just like with the neutrinos coming from the sun, whatever you do to change neutrino properties to solve that problem, you have to account for that factor of 3 or that factor of 2. So again, it could have been any number. It's amazing that it's a gigantic factor like that. But yeah, it's not something that's very important. It's just something that you can control with a parameter in your theory. But it was a big hint, by the way, of the types of solutions that we were looking for. Yeah?
How much do we know about the length scale of the oscillation?
How much do we know about the length scale of the oscillation? A lot. By the way, this plot is a great way to look for that. So if you believe that this is some effect that's turning on, you can kind of tell that it's turning on around cosine of theta of 0. That tells you the length scale for that. Of course, the other thing that's also important that's due to Lorentz invariance is whatever effect you have, it has to scale like L over E. So L over E, if you want, is the proper length of the neutrino. So these effects also depend on the neutrino energy, which explains why these neutrinos are not changing very much. They're not changing very much because their energies are very high. So they haven't had enough time, enough distance for this effect to turn on. By the way, the only other model, so if you didn't know anything, if you had never heard the words neutrino oscillations, and you were staring at these data, there's one great way of trying to fit these data, which is by assuming that the neutrinos decay. So if the neutrinos decay, that's exactly what it would look like. So it took us a little bit longer to rule out the hypothesis that the neutrinos were decaying. By the way, if the neutrinos decay, they better have mass. If you don't have mass, you don't get the decay. That's not allowed. So that would, that's still consistent with the model that I said. So this doesn't look like an oscillation, so there's nothing that wiggles up and down, but it contains information about the oscillation length, which is it tells you how long it takes, how long do you have to propagate before you start to see this effect. And that's why we know the oscillation lengths very well. So measuring the oscillation lengths is easy in some sense, because that's the effect that's turning on as a function of distance. So that's so if you have something, even if you don't understand it very well, you can ask when does it start to change, and that tells you the length where it changes. It's much harder to tell you the amplitude of the effect, because the amplitude of the effect requires that you understand very well how much you had to begin with. And that's a little bit harder. That depends on the Monte Carlo. By the way, the dotted line here is the oscillation fit to these data, of course, which works quite well. So any other questions? Okay, so I think I could stop here, and then we could all go to lunch. That sounds like a good plan. All right, thanks.